Okay, so in this first video we're going to review limits, the definition of continuity, vertical and horizontal asymptotes, as well as the definition of derivative. Okay, so how do we want to approach limits at this point of the year in reviewing for the AP exam? So the limit as x approaches 3 of 3 minus x over x squared minus 9. We always approach limits by direct substitution. We replace x with 3, and when we do that, we get 0 over 0. Remember that if we get 0 over 0 or infinity over infinity, we may call L'Hopital, which is the derivative of the top over the derivative of the bottom. It is not a quotient rule. L'Hopital's rule is the derivative of the top, which is negative 1, and the derivative of the bottom is 2x. And then you take the limit as x approaches 3 of that piece, and you'd get negative 1 over 6. The other way, you know that when we have an indeterminate form of a limit, we may either factor, multiply by a conjugate, or get a common denominator. So here, we could factor out the bottom as x minus 3 and x plus 3. To make these the same, we can cross this out and take a negative, and that will leave us with x minus 3. These here divide out, replace x with 3, and get negative 1 over 6 that way. Okay. Another example is the limit as h approaches 0 of the square root of 9 plus h minus 3 all over h. So if we replace h with 0, we get the square root of 9 is 3, 3 minus 3 is 0, 0 over 0 we may call L'Hopital again. The derivative of the top would be 1/2 times 9 plus h to the negative 1/2 times 1, and the derivative of the bottom would be 1. The derivative of h is just 1. Remember, in taking this derivative, change this to the 1/2 power, drop down the power, repeat the inside, decrease the power by 1, and the derivative of the inside is 1. So then now we never evaluate negative exponents. We make that 1 over 2 root 9 plus h. Replace the h with 0. The square root of 9 is 3, times 2 is 1 over 6. In this one, to do it the long way, we would multiply top and bottom by the conjugate, which is the square root of 9 plus h plus 3. And remember that we always multiply out the conjugates, so that this times this would be 9 plus h. The outer and the inner would drop out, and this times this is negative 9. And we would not do anything to the bottom other than just squeeze them together. These drop out, these divide out, and we're left with over on top 1 over. And when h goes to 0, we get root 9, which is 3 plus 3 is 6. So there's that way as well. Next, limits to infinity. The limit as x approaches infinity of e to the x over ln of x. Well, again, we approach limits using direct substitution. If we put it infinity, we get e to the infinity over the ln of infinity. They're both going out towards infinity, although the top grows faster than the bottom. Because remember e, the graph of e looks like this. You know, when x is 0, you get 1. And the ln of x, remember the key point, when x is 1, the ln of 1 is 0. So that's ln. So out towards positive infinity, this is going towards infinity, this is going towards infinity. So it is L'Hopitalish. We can do the derivative of the top, which is e to the x. The derivative of the bottom is 1 over x times 1. But you want to invert and multiply this. Clean that up to make this e to the x times x. So now if I take the limit as x goes to infinity of this piece, I would get this to be infinity, and then e to the infinity is infinity, and infinity times infinity is infinity, or it does not exist. And remember that when we take limits to infinity, both positive and negative infinity, we apply what is called the dominator theory. Who dominates? If the top dominates, the answer is a D and E. If the bottom dominates, it's a 0. And if they both dominate equally, both the top and the bottom, then it's the coefficient of the top over the coefficient of the bottom. Definitely E grows faster than ln, so therefore that would be a D and E. Exponentials pretty much grow faster over all the functions we have. They grow the fastest out of a lot of the functions we have. Next, the limit as x goes to infinity of x squared times x minus 1 all over x squared plus 1 times x squared plus 3. If you put in infinity, you definitely get infinity over infinity. So you can do the L'Hopital's rule by cleaning this up and taking the derivative of the top and the bottom. Or just realize that on top, you're going to have x cubed plus these smaller terms of lesser degree. And then here on the bottom, you're going to have x to the fourth plus terms of lesser degree. So here in this one, the top dominates the x cubed. Well, the x cubed will dominate in the top. The x to the fourth will dominate in the bottom. The x to the fourth wins, so the answer to the limit would be 0. Okay. Next, the limit as x approaches infinity of, say, sine x over e to the x. Here in this one, who would dominate out of the two? Remember that sine is bounded between plus or minus 1. Those y values are going from -1 to 1. That's the range of sine, as well as cosine. And e to the x, that's going to grow pretty fast. So big numbers in the bottom, with only numbers going from -1 to 1, is going to yield 0 as a limit. And next, two common problems that are often missed is with exponential functions. The limit as x goes to infinity of 3 to the x minus 1 all over 1 minus 2 to the x. Well, again, by direct substitution, we'd put in infinity, and we would get infinity over infinity. You can do L'Hopital's rule, but remember that the derivative of an exponential function is the function itself times the element of its base times the derivative of the exponent. And the derivative of the bottom would be -2 to the x times the ln of 2 times 1. And you're still going to get infinity over infinity, so you can be there for a while because the derivatives of exponential functions are always the functions themselves times the ln of the base times the derivative of the exponent. So if we just look at this by inspection to see who dominates, well, on top it's going to be 3 to the x, and on the bottom it's going to be -2 to the x. But which of those two dominates overall? It's going to be 3 to the x. So then therefore that will be a D and E, or it does not exist. Now if we were to take it towards negative infinity, that changes everything. Because when I replace x with a negative infinity, remember, we cannot evaluate negative exponents, make them positive. This would be 1 over 3 to the infinity minus 1 over 1 minus 1 over 2 to the infinity. And 3 to the infinity is 0. So this piece will be 0 minus 1. This piece will be 0. 1 minus 0 will be 1, and the answer is -1. So remember that when we take limits towards both positive infinity and negative infinity, these also represent horizontal asymptotes. We find horizontal asymptotes by taking the limit towards positive and negative infinity. So here, a horizontal asymptote would be y equals -1 in the negative infinity direction. In the positive infinity direction, we don't have a horizontal asymptote. We always don't have to have, two horizontal asymptotes. We can only have one perhaps in one direction. Like an exponential functions a lot, out towards negative infinity, we approach 0. We don't always have to have two. Okay, next. So on that matter, let's find some horizontal and vertical asymptotes. Suppose we have f of x equals x minus 1 times x plus 2 all over x minus 1 times x plus 3. Okay, vertical asymptotes occur where the denominator equals 0 after you have simplified. Well, this function simplifies and reduces to x plus 2 over x plus 3. So therefore, there's not a vertical asymptote at x equals 1. There's only a vertical asymptote at x equals negative 3, because this simplifies and drops out. The horizontal asymptotes, in taking the limit as x goes towards positive and negative infinity of f, well, on top you're going to have x squared plus terms of lesser degree. On the bottom you're going to have an x squared plus terms of lesser degree. Both the top and the bottom are the same. They both win, it's a tie. So it's the coefficient of the top over the bottom, or 1. So the horizontal would be y equals 1. And in that case, the limit is the same towards both positive and negative infinity. I don't have any negative exponents here to worry about, so it's going to be the same for both. Next. Now, what is at 1? I just erased that problem, but what is at 1? There's still a hole there at 1. There's no vertical at 1, but there's a hole there, because that denominator, even though the x minus 1's drop out, that denominator can never be 1. It's always based upon the original function and not any simplifications. So again, to clear things up, vertical asymptotes, you set the denominator equal to 0 after you've simplified. If something did drop out, like in that case, there's not a vertical there, there's a hole there. And the horizontal, we take it towards both positive and negative infinity. Okay, so suppose we have this function, the quantity x plus 1 squared times 2x plus 3, all over the quantity e to the x times x plus 1. Okay, vertical and horizontal asymptotes. Vertical, notice that these drop out. So therefore, x equals negative 1 is not a vertical. Does e to the x ever equal 0? No. So there is no vertical asymptote. But there is still a hole at x equals negative 1. There's still a hole in the graph at x equals negative 1. Horizontal asymptotes, if I take the limit as x goes to positive infinity of f, well, on top I'm going to have here an x squared eventually, if I square that, times a 2x plus 3 is going to leave me with like a 2x cubed on top. And on the bottom, I'm going to have just this, e to the x times x plus 1. I can't simplify that really anymore. So towards positive infinity, this dominates on top, this dominates on the bottom. The bottom wins, so it's going to be equal to 0 in that direction. Now, what about towards negative infinity? We'll have 2x cubed over, towards negative infinity, this would be 1 over e to the infinity times x plus 1. So then 1 over e to the infinity is going to leave me with infinity, which is 0 in the bottom down here. So 1 over infinity is 0 times this, so that's not going to exist at all. So we only have one horizontal asymptote, horizontal asymptote, and that would be at y equals 0. Remember, horizontal asymptotes are y equals a constant, and verticals are x equals a constant. So in that one there, in taking it towards negative infinity, e to the negative infinity would be 1 over e to the infinity, which is infinity, and 1 over infinity is 0. And 0 times this is going to be 0, but a 0 in the bottom just does not exist, so that limit's not going to exist. Okay, so there's a brief review of vertical and horizontal asymptotes. Verticals, simplify first, set the bottom equal to 0. And horizontals take the limit towards positive and negative infinity. Continuity, very importantly. Let's review the definition of continuity. We have 3 things for the definition of continuity, and they must be clearly shown on the test, especially in a free response. To be continuous at x equals, call it c, f at c has to exist. The limit as x approaches c of f of x has to exist. And the limit as x approaches c of f of x has to be equal to f of c. 3 things. You have to show that the function value at this number exists, that the limit as x approaches this number exists, and that the limit value equals the function value. 3 things. Function value, limit value, and they must be equal. So for example, in an application, this is a common multiple choice problem. F of x equals the ln of x plus k for 0 less than x less than 3, and it equals the cosine of kx for x less than or equal to 0. Okay, so in finding the value of k so that f is continuous everywhere, we will take the limit as x approaches 0 from the left of f and set that equal to the limit as x approaches 0 from the right of f. So this is of concern, the breaking point in the domain. So if I put in 0 for x, not k, but for x, I'd get the ln of k equals 0 into here is the cosine of 0. Cosine of 0 radians is 1. So the ln of k equals 1. Base e both sides. And k would be equal to e. So that would be the value of k so that f is continuous everywhere. Okay. Next is continuity and differentiability. So if I have a graph of a function here, this is 0, 1, negative 1, and just suppose we have something going on like this, right through here, like that, and I believe I have an open circle here, and it looks like this. And just suppose this here is out at 3, okay? Okay, so is f continuous at 3? Yes. Just suppose this is a y value of 2 and this is negative 1. It is continuous at 3 because f at 3 equals 2. The limit from the left of 3 and the right of 3 is 2, and that limit value equals the function value. Is it continuous at 1? No. There's a gap here, but for what reason? It's that the limit does not exist. The limit from the left of 1 is negative 1. The limit from the right of 1 is 2. Therefore, the limit as x approaches 1 of f is a DNE. Is it continuous at 0? Yes. Is it continuous at negative 1? No. And the reason being is that f at negative 1 is a DNE. Remember, function values, you look for the closed circle. And then in limits, you read what y value the function's approaching as you near the x value. So as I approach 1 from the left, I'm hitting a y value of negative 1. As I approach 1 from the right side, the y value is near 2. So those limits from the left and the right are not the same, so that would not be continuous there. And while I have this up, where is a function not differentiable? At corner points, at a cusp, another sharp turning point, discontinuity, or vertical tangents. So, and remember, look to where vertical tangents often occur. They can be hard to see sometimes. Graphs that appear to get, vertical, like the cube root of x. That's a common graph that has a vertical tangent. Okay, so where a tangent line appears to be vertical, that is not where it's not differentiable there. Okay, so remember, if a function's differentiable, it's continuous. If it's differentiable, it's got to be continuous. But continuity does not imply differentiability, because think of the absolute value function. Okay, and just two more things. Recognizing the definition of derivative, very important. The limit as h approaches 0 of, say, the cosine of 2 pi over 3 plus h minus the cosine of 2 pi over 3 all over h. So, two things. What's the function? Always cover this stuff right here. So the function is cosine of x. The a value is 2 pi over 3. What the derivative is being evaluated at. So this is the function. Its derivative is negative sine x, and then I replace x with 2 pi over 3, and I evaluate the sine of 2 pi over 3. So this is 2/3 pi over 3, root 3, negative 1, 2. Sine will be root 3 over 2 times the negative. So that would be negative root 3 over 2. So remember, cover the inside stuff here. Replace that with x, that's the function. This portion is the a value. So if this were x plus h, then it would be the derivative at x. If this were a plus h, it would be the derivative of cosine at x equals a. This here is what the derivative is being evaluated at. Just another quick form. If I had the ln of 1 plus h minus the ln of 1 all over h, then again, what's the function? Cover this stuff. It would be the ln of x. What's it at? 1. So the derivative of ln of x is 1 over x. You put in 1 and you get 1. Okay. Another one that could be harder to see is 3 to the 2 plus h minus 9 all over h. That's the definition of derivative. The function is, again, cover this stuff, call it x. So the function is 3 to the x. It's at 2. So the derivative of 3 to the x is the function itself times the ln of its base times 1. Put in now the 2, that's 3 squared, which is 9, times the ln of 3. Okay? And the last theorem we've talked about in this chapter would be the intermediate value theorem, IVT, which says a function f is continuous on a closed interval AB, and given any y in between there, we can find a c corresponding to that y value. So how do we see that? Suppose f is continuous on the closed interval negative 2 to 5, and f at negative 2 equals 3, and f at 5 equals 8. So for any y value between 3 and 8, we know we can find a c value corresponding to that, so that f at c equals that. So would it be true, would there exist a c value between negative 2 to 5 such that f at c would be equal to 4? And the answer is yes. There exists at least one c from negative 2 to 5 such that f at c would be equal to 4, because 4 lies in between 3 and 8. Are we guaranteed a c value such that f at c would be equal to 0? And the answer is no. because of the fact 0 is not a y value in between there. It could, but it does not have to be true. And remember, as you tackle these multiple choice questions, that what could be true and what must be true are entirely different. That could be true, but it does not have to be true. Okay? And one more quick example on continuity. Suppose g at x equals pi times sine x over x for x less than 0. It equals a minus bx for 0 less than or equal to x less than 1. And it equals arctangent of x for x greater than 1. So find the values of a and b so g is continuous. So I'm going to need two equations if I have two unknowns. If I put 0 into this, I get the sine of 0 over 0 in taking that limit. I'm taking the limit from the left of 0. I put that in and I get the sine of 0 over 0, which is 0 over 0. Remember, that's a special limit. The limit as x approaches 0 of sine x over x is 1. Remember that ax over bx, it's a over b. Or that is L'Hopital. The derivative of sine is cosine x, and the derivative of x is 1. If you put in 0 for x, the cosine of 0 is 1. So towards the left of 0, this is 1 times pi is pi. Now towards the right of 0, I'll put this in, and I'm just going to get a equals pi already. So there's that, that's done. Now I can put the 1 in for the x, for the left of 1, take that limit, and I'll get a minus b equals, and if I put 1 into here, arc tangent of 1 is pi over 4. So therefore, the angle whose tangent is 1 is pi over 4. So I'll put that here. And I know that a is pi. So then negative pi over 4 equals pi over 4 minus pi. That's negative 3/4 pi. So b would be equal to 3/4 pi then. So b is 3/4 pi and a is pi. Again, in this one, if you have two unknowns, you most likely need two equations. So I needed to take the limit as x approaches 0 from the left and the right, and then I had to take the limit as x approaches 1 from the right and the left. The left being this case and the right being this case. And two unknowns, two equations. And that concludes the review of limits, continuity, and vertical and horizontal asymptotes.